Hi, welcome everyone. Today we want to continue our discussion on network security. A quick recap. Last time we talked about the Tor hidden service, onion routing. We first want to hide the client's IP address, and then we hide the server's IP address. So while still enable client to identify the server, retrieve the content, and post content, that was and then we also explained how mixed network works in terms of how the messages are formed. You have different layers of encryption. The sender has to do a lot of work ahead of the time, wrap it around, and so that the proxies, the relays, the intermediate routers will be able to peel off and know where to route the message. Quick feedback on homework 1. Everybody does, most of you did really great, and I'm extremely happy because this online asynchronous teaching is hard to assess how well you know, how well you follow. Extremely happy, very proud of you. For a few of you, I gave you feedback. If you want to talk about it, please come to me and we can chat about how we can help you. A lot of people are confused. Digital signature scheme only protect message integrity. Look at the certificate. Everything is public. The statement is public, so that the verifier can hash it and then confirm the digital signature. It's very important. Not the confidentiality, digital signature, no. If you want to achieve both integrity and the confidentiality, of course you can. There's a scheme that called the sign crypt, but you just encrypt first and then sign, okay? So you encrypt with receiver's public key and then you hash just as you do for digital signature and then compute signature. And they send it over, they verify the signature and then decrypt. You can do it to use symmetric key scheme as well, assuming both parties have a shared key. And you just AES to encrypt and then add a keyed hash. Okay, so usually at this point to figure this out all by ourselves. Most of the time on the internet, we have the TLS, of course, it requires both. And so in the TLS, we have this flavor thing operation going on. For public key certificate, just integrity. Tor protects privacy. Okay, it's very important. At the end of the last class, we said that there's no confidentiality built in Tor. You still have to encrypt those messages with end-to-end encryption. And a lot of people learned it the hard way. Many embassies using Tor end up revealing their password because the exit node, the exit relay would just see plain text. Okay, so please, if you use Tor, still need to, like email, still have to encrypt end-to-end the receiver's password. Today we want to say more about network attacks and defenses and firewalls, intrusion detection systems. Some of the attacks that we'll talk about are intrusions, sniffings, attack traffic, DOS, spoofed traffic. So in the network threat model, you have passive attacks, eavesdropping, those kind of thing, and traffic analysis is referring to learn about traffic patterns, correlations, or who might be sending what traffic to whom. Fingerprinting, know what versions of software you use. There's also active attack, DOS obviously, but also impersonation of an IP address, modification, relay, and so on. Firewalls is, of course, the first line of network defense. It's very important. They're also relatively easy to set up, relatively easy. In practice, everything is complicated. And in textbook, we learn about the concept, the high level. When you go to work, if your job is to set up firewalls, you have to be careful. Common defenses, like a lot of the, by now you should have already get a sense of, okay, a lot of times that the defense is in the flavor of monitor, filter, screen, block, network segmentation, isolation, you know, those kind of the typical approaches. Firewall can allow you to specify rules, the kind of traffic that are allowed to pass. There's stateless and stateful firewalls. Stateless is like HTTP. We forget about what happened before. We just look at this particular packet, allow or deny. Stateful is more complicated. We remember, you know, ongoing traffic, the sessions, ongoing sessions, and so you have to have a table of some sort. Stateless packet filtering, you look at header, port number, addresses, some of the TCP flags, and then you determine. And see, here are some very simple examples of the firewall rules. People call it access control list, and on the first column, you have allow or deny, and by default, we want to deny everything. And then you see the second column is the source address, source versus destination, and this will depend on is this incoming traffic or outgoing traffic. Like the first rule, this is the source is within the organization, the destination is anything outside, then that makes it outgoing traffic. The second rule, reverse, that means it's incoming traffic. The destination is within the organization, right? So port 53 is a DNS port, the default DNS port. DNS also use UDP. It's unreliable, but most of the time it's fine because it's very small. And so this means that incoming, outbound DNS traffic are all allowed. First two rules are for port 80. And it sounds like HTTP traffic are all allowed both ways. The second rule has this interesting flag bit requirement. Is if ACK bit is on, then it's allowed. So we'll explain why that's the case. Deny all is the last rule. The first rule basically says outgoing requests to external web servers are all allowed, and so means employees can serve, okay? Because the source is within the organization. In this example, is, you know, the destination is outside, so external web servers. Destination port 80. You know, you may ask, okay, what if the external web server does not run on port 80? Well, then that's weird, because most of the legitimate web servers would run on port 80, the default port. Then non-default port would actually indicate there's something fishy going on, so will not be allowed. Incoming traffic from external web servers are allowed, the only when it is responding to some earlier outgoing request from a company employee. That is why the ACK bit is set on. And recall our TCP handshake. The first step is for the client to send a SYN request, and then server respond with a SYN ACT. And then all the subsequent packets will have the ACK acknowledgement bit set on, set to 1. So this rule with this last column requirement, that means that, you know, it has to be, we only allow external traffic, web server traffic, when it is responding to an internal request. And so that is something that could be spoofed. We'll talk about that in a few minutes. 53, this is DNS port. Most time that all the servers are allowed, and my student find this out. And then there's also, of course, this is, you know, known for a long time. And then we did some work to demonstrate you can actually use this called DNS tunneling to send encapsulated command and control traffic. And so it looks like DNS, but it's actually for botnet command and control, or whatever, HTTP in whatever email. And so you can, this kind of encapsulation that we talked about before. But then what else can you do? Okay, it's DNS. If you block DNS, then well, you pretty much you will receive a lot of complaints. So typically don't block the DNS. Stateless filtering, there's some other examples. You can have different aspects, inspect different aspects of the headers. This firewalls usually inspect header. They don't do deep packet inspection. They don't look at the payload, of the application layer. So as I said, the ACK bit can be forged, right? So just some bit in the traffic, you can set it, anyone can set it to 1. So attacker can pretend to be responding to an earlier request of the user, but then it's not really of any ongoing session. Okay, and then that traffic would be allowed. Like if you do network reconnaissance per scan and so on, you can just set this as port scan may not be good because you have the port already set. You could be able to scan certain port on the client side. Yes. So you pretend to, attacker pretend to be the web server coming from port 80, and then you are scanning client side non-privileged ports. So this is bad. So there are some deficiencies for stateless firewalls, and that's why a more advanced one is a stateful firewall. So where you can keep track of ongoing traffics and what traffic makes sense. So you have a little bit of memory. In this case, we have a new column with a check connection table, and then the firewall would maintain a separate table that keep track of all the ongoing connections. And so whenever the client, the internal client, starts the connection, and then we start entering an entry on the connection table, and then we have some responding traffic coming over, incoming traffic, and then we see, oh, this is making sense. So and then the more you do this, the more you realize, okay, maybe we can do a lot more. And then one of it is called intrusion detection systems, IDS, which you can also check, packet information, correlations, content screening. And you don't need to have just one. You can have multiple. You have firewall, first line of defense, and then you can install intrusion detection. People call it IDS sensors, but then it's can be software or appliances, and just screen traffic, right? And hopefully they don't slow down traffic too much. So you do have to balance the performance. Most importantly, it does deep packet inspections, look at for characteristic malicious strings and virus signatures. Can also see, oh, is this external a bunch of traffic doing port scan? Okay, it just visit a whole bunch of random ports within a short amount of time. And so you can do this kind of more aggregated analysis. SNORT is an open source intrusion detection systems. It has community contributed rules. IDS is passive monitors traffic, and so there's another more advanced system called intrusion prevention system, IPS, that can actively block and filter out traffic, remove attachment, and so on. And a lot of times that you don't know which one you're running, and then people will say IDS/IPS, and so it's just a similar type of products, security defense products. But it can do a lot of things on its own, and so because otherwise, if you allow traffic to go in, and they may already does a lot of damage. And so of course, if you have false positives, that means you have false alarms and you remove an attachment and then, that may not be ideal. So there's always issues. Concerns that you have, when you design the IDS and IPS. False negative is where you miss a detection, you miss detecting something is also undesirable. Here are some examples of this Conficker worm, which I think around circulating maybe 12 years ago. The top half is the encrypted version, the bottom half is decrypted. They use the XOR key. They just do XOR and to mask this. If you do XOR again, you retrieve the decrypted shellcode, and then parts of it can be used for signature, as a signature, and then you just scan it. And so if in part of the signature here is the HTTP, and of course it's but that by itself cannot be a signature because you generate so many false positives, and it has to be in combination with anything else, in certain special URLs, and that's usually it can be used as a signature. So it doesn't have to stop. You don't have to stop as detecting malicious patterns. And sometimes you can use, it's a string matching, pattern matching. You can detect whether you have sensitive information being leaked without encryption, right? People accidentally email attach sensitive files. And so we have done some work called the data leak detection, and you can outsource as a service. We have this privacy preserving aspect built in, and so that the detector could be a third party, could be a cloud provider, can perform the detection without knowing what exactly is a sensitive pattern. And so another network defense is called anomaly detection. Of course, it doesn't have to be for network traffic, can be also for system calls and so on. Anomaly detection is extremely powerful, and this probably is something that the most fun slide of this lecture. Gangnam Style was, I think, the first YouTube video that hit 1 billion views, and then people from Google at the presentation, they mentioned there was certain days the views just spiked, and it was really unnatural and didn't follow any for sound distribution and so on. Some of the views were removed, and so detecting fake views, right? How would you detect fake views? There may be you look at, okay, does the user have any other visits before visiting YouTube, and what did they do leading to this visit? If it's bot, then it's just go straight to loading this page. Insider trading detection, and so all of these are very interesting, very very challenging topics as well. And so a lot of times that is challenging because it's obviously easy if it's extremely obvious. But then, a lot of people, they know that you're detecting, insider trading, so they're actually doing something to stay under the radar and make it harder to detect. And a lot of times that for this detection, people don't report the accuracy. So you don't know, okay, they say, oh, we detect this, but you don't know how many things are missed. And so it's just very challenging. For network traffic, of course, you can look at unusual traffic volume, size, ping of that, and we talked about that. It potentially can detect new attacks if the attacker does not have a copy of your detection algorithm, and then therefore cannot circumvent you, and will have to learn to bypass your detection. But it's difficult false positives all the time. We have done a lot of work to reduce false positives, and then I think the high level key is just to understand your traffic. If you understand your traffic, and you use some patterns would emerge, and then you capture that, and then you detect the deviation from that pattern. And a lot of times that you also have to only flag those that have consistent anomalous behaviors, and like first offender, let it go. But then of course that could be false negatives, miss the detection. So we talked about TLS, right? The HTTPS, and then there's almost at any level, not almost, virtually, I mean, for every level of network stack, there is a secure version of that protocol. And when the network stack protocols were designed, nobody thought of 30 years later there will be like so many attackers. And so it's always like add-on. The security is always add-on and network layer. IPsec protects the authenticity of IP packets. That means that you get IP packets from a router. It's indeed from that router. Confidentiality, you protect the content, and so therefore people can now learn the IP address, right? So you want to hide the IP address sometimes because that if you expose your IP address, people may launch denial service. So authenticity and the confidentiality is provided by IPsec. So we just want to quickly at a very high level see how it is done. And before we go into, you should be able to kind of guess how this could be done, right? I mean, how else could this be done? There's only a handful of ways. You either public key, you have private key, and then you sign, you encrypt, right? So that's exactly what was happening. Authentication header is where you have data integrity protection, and so you have there's no encryption of the content, but then you have the integrity check code. It's a special mechanism to make sure that there's no one who can modify the content, and a more complicated mode, the ESP mode. It's the full mode of IPsec. It allows encryption as well, and the payloads get encrypted. And of course, use what keys. So we'll talk about keys in a minute. And we said that okay, we need to hide the IP address. Sometimes this is an option. It's not always required. It's tunneling mode. Tunneling mode will allow you to create a new IP header, a brand new IP header with a new address. And so, part of the old address is hidden, the real destination address. So of course, a new address has to make sense. It has to go to an actual proxy, a gateway. And the gateway knows, has some key to peel off this new header and then be able to reveal the real header. And so that the delivery still can be made, but then everyone on the path, on the route, won't be able to see the actual specific header on tunneling mode. We have seen this, we talk about VPN and so on, it's very similar. So new header is being highlighted in that animation. Transport mode is a lot simpler. It just transport mode would not generate a new header, but then just allow you to have this authentication information and then additional security headers to be attached to it. Okay, but then the payload stays. So you see there's like several orthogonal version. There's security-wise, you have two options, and then transportation-wise, you have two options. Why? So it's altogether you have four options, as this table shows. Depending, how what is your threat model, what is your security goals. Of course, none of this would work if you don't have keys set up, right? So you can certainly encrypt, but then people need to decrypt it. People meaning that the routers, right? The IP level is just the routers are handling the they in terms of encapsulation, they decapsulate up to the IP level. And you can set up manually or set up automatically, and there are protocols again, more protocols to help you set up between routers. A lot of this is done using shared keys, pre-shared keys. For automatic fashion, you do have to have public keys and so on. Yes, then go back to similar to TLS. So I'm not going to go to details, but then by now you should conceptually be able to figure this out, how this is done. And of course, in reality, there's a lot of many complications, and including TLS. Right now we have 1.3 version, but then 1.2, the version already, people find so many issues in the implementation. The design is all good. So there's a huge gap between theory and practice. Hence, email, I'm not gonna go very details, but then do understand that between you and the mail receiver, there's at least 2 mail servers. I mean, there are at least 1 mail server. If Alice and Bob are in one organization, then there's 1 mail server, and then there's also routers in between. If you send something to California, there's a lot of entities touching your mail, and so there's a lot of confusions. Even from security experts, they say, "Oh, I don't have to encrypt my email." Because it's already having end-to-end encryption. It's already encrypted. It is encrypted, all right, but then it's not end-to-end encryption. End-to-end, what does it mean? One end is Alice, the other end is Bob. If Alice does not use Bob's public key or some other key to encrypt her message, then there's no end-to-end encryption. There is some encryption between the hops, between your computer to Gmail server, and then between Gmail server to maybe Purdue.edu's mail server, and then between Purdue.edu's mail server to Bob's computer. So, but then they do decrypt. The mail server do decrypt your message. That's why Gmail has all the messages you have, and then if you're under government federal investigation, they will be able to provide all your email records to the government, and so it's not end-to-end, and you may not need end-to-end. Very few people need end-to-end email, but it's very important to know the encryption is only at particular segments. At the end, we want to talk about, at the end of this class, we want to talk about the domain name system, which is, we said that it's communicated using UDP on port 53. It's implemented as application layer protocol, and then you just basically, everyone needs it. Otherwise, we don't know the IP address of servers. We only know Amazon.com, but then it's not very useful for computers. Computers need IP addresses. And DNS is distributed, is hierarchical, and it's just very well defined and very robust. If you think about everyone need to visit DNS. If you visit a new website, your browser need to first resolve the domain name, get the domain name resolution. Centralized system does not work. Single point of failure, single biggest bottleneck vulnerability, not very scalable. And so it's distributed very widely. I mean, this is the design, the domain hierarchy. Okay, so you have a .com domain, which then divided into company have subservers, and then you have edu and so on. And so in US is lucky, does not have country code. Many other countries have country code. We're talk about several so NL, Netherlands, right? SE, Sweden. We'll mention those two countries later on today. So many name servers is distributed hierarchical database. Okay, and you don't need to have everyone's name translation, IP translations. You only need to know the ones that you are in charge of, you're responsible. For example, vt.edu's name server need to know the cs.vt.edu's IP address. Okay, so if anyone want to visit cs.vt.edu, they would go to edu, find out what IP address corresponds to VT, and then go there, go to vt.edu's name server, find out which one is corresponding to CS. Okay, and then they go to CS, and they would be able to find out. You may have to go to CS to find out www.cs.vt.edu. And so no one knows everything, but then they know a little bit, and so that just you can resolve this eventually. To get things started, you have root name servers. Of course, almost very rarely you have to query root name servers, because all our queries are resolved by local name servers, has tons of caches. And so and only when you have new domains that you don't know, then your local name servers have to query the root name servers. And many fault tolerance mechanism to ensure name servers. And even it says 13 root name servers, but then there's also multiple locations, and there's actually more than 13 physical machines, which is absolutely necessary. And so you have top level domains. It's just some more terminology. TLD, responsible for all those like big domain, top level.com.edu. Authoritative DNS server are organizational name servers, right? The VT has its own authoritative name servers. Most of the time, ISP, Verizon, Comcast, and they have their local name servers, and lots of cached content, and so it's a lot faster to cache, and there's also time to live associated with DNS record, and so if this expires, and then you refresh your record. Just very quickly, this is just has nothing to do with security. I mean, it has very little to do with security, but just DNS general knowledge. You can do iterative queries where the local name server will just keep querying until things gets resolved and then return to a host. And of course, the DNS server, the local name server will do a lot of work. And then you also have recursive query, and you have the root server will get this resolved and send it back to the local name server. They have different type of performance overload workload. In general, if you have more workload, then you're more susceptible to the denial of service attack. And similarly, if you keep like half opened connections, and then you were wasting memory, that could also create vulnerabilities, like we talked about SIM flood attack, like half opened jobs. And so here are just some commands for you to play with DNS. DNS cache poisoning is something that I want to mention here. What does it mean? And a lot of times that DNS records are cached just for performance purpose. And then, it's just a lot of people they all use Amazon.com. They all use similar, Facebook.com. But then if that information, the cached information is spoofed, it's not authentic, it's injected by the attacker, then the victim may be visiting an attacker's website, a phishing website. And so how is this possible? Typical, DNS by itself has no security. DNSSEC is a separate security version of DNS. Its adoption is better, not 100%. And with no security, of course, you don't know who you're talking with. You thought you're talking to vt.edu's authoritative name server to get certain IP, but then you might be talking to an attacker. The traffic gets, attacker just feeds UDPs in a huge amount of UDPs, and then you eventually get that you being the DNS, the vulnerable DNS server will accept that as an authoritative record. And then the next time any user or query the same domain will retrieve the wrong IP address and then end up visiting an attacker's website. So then you have the name server, the vulnerable name server has a poisoned cached record of DNS. So the root cause of course, there's no authentication in among name servers. And in order to authenticate, you have to know, okay, am I talking to the right name server? And there may be some keys involved, and just like what we did in TLS. And that's exactly what's necessary. DNSSEC is called the Domain Name System Security Extension. It ensures integrity and origin, right? So it's authenticity. There's no particular confidentiality involved, because a lot of all this information is public. So of course we have to require name server to have keys, and then they would create signatures on record. Okay, on DNS record, and this is, says this domain name translates to this IP address, and then, for every record you have signatures. Besides the typical translation, you also send a signature, user verifies, and user also need to verify the signature is correct with respect to the correct public key. And we all know whenever we say correct public key, and then this is not as easy as we thought, right? Where to find the correct public key? If we find it we use the wrong key and go back to square one. Well, in terms of storage, DNS is a database. DNS has a place to store records. So the key can be stored on the DNS server, and you just query the key. And there are certain names for you to name that entry. So you can call it a key.cs.vt.edu pub key, or DNSSEC, DNS key. There are multiple keys. So you can retrieve the key, but then as in TLS, you need to have some sort of certificates. And in DNS, we ask the parent zone to sign the child zone's DNS public key to endorse it. And you have the grandparents zone sign the parents zone, and then so you go all the way to the top, and that forms a chain of trust. And similarly to the CA sign the public key, you have for first level CA and a second level the root CA similarly. So for this adoption, for DNSSEC adoption, it's very important. This key signing chain has to be followed. And then you store information on the DNS server. So very similar, and so it's important for us, all of us, to understand the TLS, and because a lot of the concept is very similarly used. And of course, in reality, this is far from this simple. Okay, in reality, there is if you look at the DNS specifications, there's like multiple types of keys. You sign the record using one key, and then there's there's a key generating key, and then you have to sign that key. And so if one key is changed, then the other key is not changed. There's like long-lasting key and a short-lived key for key management usability. Very complicated. It's not impossible, but then you have to really prioritize security in order to start do it. TJ Chang is our professor in our department with specialty in network security. He has a very interesting work, and he measured the adoption of DNSSEC in Europe, in some European countries, in particular. Here, the figure shows two registrars in European-based. One is Dutch-based KPN, the other is Sweden-based Lupia. And you see here, the y-axis is adoption percentage. Higher the better. But most of the you see, okay, it looks like there's just only two lines. You have Netherlands adoption in this .nl. Netherlands domains adoption pretty high, 80%. Well, very well done. And then everybody else is 0%. And then you have here from Lupia, same thing. Everybody else besides Sweden is 0. Even Netherlands adoption is 0. What's going on here? It turns out that there are some financial incentives from the government. For example, KPN receive like 30 cents, US cents discount if they can correctly install the DNSSEC record for a .Netherlands domain. Okay, and this is like from the government. The government want everyone to use DNSSEC. And so the Lupia receive a lot more, $1.10 for any correctly signed Sweden domain. So it's, you see even higher adoption, like almost, it look like 92%. So financial incentive does work. Otherwise, it's tough. And GoDaddy and OVH are the registrars. Registrars, they can provide free. They may or may not provide free DNS support. GoDaddy charge $35 per year. Not that high, but then still you see. I remember it's not 0, it's like 0.2 or something. OVN, pretty good. I mean, it's not 0, it's like 26%. But it's encouraging to see the trend is increasing because it provides DNSSEC for free. A customer does have to opt in. That means by default it's not enabled. You do have to say, I don't want to have DNSSEC. So that is also, I think the security, this just touches on the security and economics. And so if there's sufficient incentives, people do want to adopt security tools. So I encourage you to read about this. I have links in the previous slide. And so there are a lot more other interesting findings from TJ's paper. So that's it for today. I want to end it now. I also have a very quick written homework coming out. I know you're already having a programming assignment, but this is going to be a very short one. So, all right, that's it. Thank you. Bye.